One of the coolest applications of the Hardy-Littlewood maximal function is a simple proof of Lebesgue differentiation theorem. I am following the book Lectures on Analysis on Metric Spaces by Juha Heinonen, and I will be following the argument there verbatim, and also the statement will follow that terminology. I feel a little bit not too happy that I'm basically copy-pasting part of a textbook here, but this proof is so elegant that I just couldn't resist, so hopefully this will motivate you to read up more on both Lebesgue differentiation theorem and the Hardy-Littlewood maximal function. So the particular statement in the book is as follows. Suppose you have a doubling metric measure space, which was needed for the maximal function theorem to hold, and that continuous functions, notice that notion of continuity requires the metric d, and notion of doubling has to deal with the measure mu. So continuous functions, we assume, are dense in L1 of x with respect to the mu. That means dense in the L1 sense. In the proof you will see exact meaning of this density. Then, if f is locally integrable, this was the type of objects on which the maximal function is defined, on x, then the familiar Lebesgue differentiation theorem equality, that the lim sup as r goes to 0 of the average oscillations of the function d mu with respect to y is 0. So you integrate over the ball, so this for almost every x in x. So this quantity, you fixed x, and then you integrate over the ball of radius r centered at x. You take average. This quantity, the differences of f values from this fixed f of x. So this is fixed, and y is the integration parameter. So this is d mu of y. So this quantity is equal to 0 as r goes to 0 for almost every x. So that is the statement of the Lebesgue differentiation theorem. Notice that from this star, we can deduce the following, that for almost every x, indeed for the same exact x's as the one that the star holds for, the limit integral average of fy, actually we can just drop this over bxr as r goes to 0 is none other than f of x. Let's see why. Because, so let's compare f of y. Let's forget average because, okay, well, integral average of fy, so this is with respect to d mu of y, of course, d mu of y. So we're trying to show that this integral, when r goes to 0, it goes to f of x. So we just compare this difference, and we want to try to show that this quantity goes to 0, right? As r goes to 0. So that is the meaning, the definition of limit, indeed, from whatever calculus or algebra. But this quantity, this is a constant value. So if I integrate b, x, and r, fy dy, d mu of y, so this is the first integral, but then I can just put this integral average inside. So this was integral average. This is equal to this one because, again, f of x is a constant because integration is with respect to y. and it just comes out, and this averaging means it doesn't matter what size of a set we are integrating this over. But then you can see that integrating by first taking the absolute value. So this is integral of some function. So this is integral of this quantity, then absolute value. If you put the absolute value inside and then integrate, you get something that is at least as big. The averaging doesn't change that. It's just in the denominator, and d mu of y. But then this goes to 0 for almost every x for which star is true. This goes to 0 as r goes to 0 for x's for which star holds, just for you to see. So if this is true, then this goes to 0, so does the smaller left-hand side. That means this quantity goes to 0, which is equivalent to this integral converging to that. So sometimes this is the familiar statement of the Lebesgue differentiation theorem, that averages of the function converge to the value at that point if this average is being taken over smaller and smaller balls centered at x. But again, this star is a priori a stronger statement than the next one, the double star. However, actually, you can get from double star back to star also, at least in the Euclidean case, very easily. Okay, now the proof of Lebesgue differentiation theorem using the weak type estimate for the maximal function. So what happens is when f is fixed, so f locally integrable is given, we want to show that this quantity, lim sup, as r goes to 0, of b, x, and r, absolute value of fy minus f of x. Remember, x is frozen, y is the quantity. We want to show that this is equal to 0 for almost every x. So Hayden gives this the name, lambda f. This is a new function evaluated at x. So here we defined this functional. So given f, we create this functional lambda f, which is a new function, and its value at x is precisely given by this formula. The claim is that, number one, lambda is sublinear, which means that if you have two locally integrable functions, f plus g is less than lambda f plus lambda g, in the sense that this is true at every x, when evaluated at every x. This shouldn't be difficult just from the triangle inequality, because you split the absolute value into two. Okay? Number two is that lambda of g is just zero function for continuous g. And why is this true? Okay, if g is continuous at x, then for every epsilon positive, there exists our delta positive such that distance, we are on a metric space, distance of yx less than delta implies the values of g at y are not far away from values of x, g at x. But then from this, it means so every single gy is within gx plus minus epsilon. So this means integral average over bxr. The averaging is nice because then estimates just hold no matter how big or small the measure of the ball is. So g of y minus g of x d mu of y will be less than epsilon. It's actually epsilon times measure of the ball, then divided by measure of ball, it goes away. But this epsilon was arbitrary, which means that this quantity is 0. Something that is smaller than every epsilon is strict indeed, is 0. Okay, so two claims about this functional. It's sublinear and it vanishes identically on continuous functions. And the third one, property for this lambda, again very easy from definition, is that this lambda f, again pointwise, that means evaluated at every x, is smaller than the maximal function of f plus the absolute value of f. So why? It's very simple. Integral average of bxr of f of y minus f of x dy, d mu of y, is smaller than if by triangle inequality, which we already have used implicitly at one incidence, plus the integral average over bxr of absolute value of f of x d mu of y. But again, notice that this is just a constant function, so integral average is none other than that constant quantity. So this is f of x, but remember that this is one particular integral average over one ball centered at x. Maximal function of f evaluated at x is supremum over all such r. So that's the good thing about maximal function, and actually the motivation why we have it. We define such a huge value that automatically every time you have one particular average, integral average, it's smaller than the maximal. And the maximal function is super useful because it says that although you define this huge functional MF, it's still bounded in LP, and we will use it in a second. So this inequality, this is true for every R. So if you take lim sup, again, this holds. So if you want to really finish this, you must say, now take lim sup as r goes to 0. Notice that this side is independent of r, so the bound persists. Okay, three properties of this lambda functional. I don't want to go back up and down a million times. Hopefully you remember what happened. So how do these three very easy properties end up proving the Lebesgue differentiation theorem? Okay, our local integrable f was given. Let f be locally integrable as given. For now, let g be any continuous function. Again on x. Now for t positive, which is again arbitrary, we have, so the measure, well, before that, the set where this capital lambda f evaluated at x is bigger than t, look that this quantity lambda was bounded by this. If you have this thing bigger than t, that means one of these guys is bigger than t over 2. And this is like one of those elegant tricks in analysis that just, it's so basic, but it works like magic. You have added two numbers and they are bigger than t. One of them, it has to be bigger than t over 2. So this is a subset of the functions mf, the points x where mf of x is bigger than t over 2, or the parts where f itself is bigger than t over 2. Except that I actually, so this is true for every function. We want to apply this to not to f, but to f minus g. So first of all, the set where lambda f is bigger than t is the same as where is a subset of lambda f minus lambda g bigger than t. Because remember g is continuous, so this is just 0. So this is, well, equal. But then this is a subset of. Now sublinearity comes in, that the lambda of f minus g is less than or equal to this quantity. So you get a bigger set by requiring this this quantity to be larger than t compared to the previous one. Okay, yeah, sublinearity. So this is a subset of that one. Now we apply this line here that I said is true for any function, so including for the function f minus g. So this will be a subset of places where maximal function of f minus g evaluated at x is bigger than t over 2, union the set where f minus g absolute value is bigger than t over 2. So hopefully you see how this is exactly this formula, except it's applied to f minus g instead of just f itself. Okay, now we have an inclusion of sets from which we see that the measure of the set where this lambda f is bigger than t. Remember, what we're trying to show is that this lambda f is actually 0 almost everywhere. So we want to say that the set where it is not 0 cannot have positive measure. This is the proof. So the measure of, so it's kind of a proof by contradiction. We're trying to say, okay, what will happen if this set is large? And we're going to show that this cannot be the case. So this set will have measure at largest equal to the measure of the set where the maximal function of f minus g is bigger than t over 2, plus the measure of the set where f minus g is bigger than t over 2. But now comes the first and last time, actually, we're now using the Hardy-Littlewood maximal function, the weak type estimate. The weak type estimate was giving us a bound on the size of the set where a function can be, the maximal function can be large. And that was controlled by a constant divided by this quantity you have here. So this would be 2 over t, but, well, 2 is absorbed into this constant. So there will be a constant over t. And then it was integral over the whole space of the function whose maximal value you're looking at, f minus g d mu. How about this set? So the set where the function f minus g is bigger than t over 2, if you multiply this quantity by t over 2, you're getting at least the okay, simply from definition of integral. Okay, so this is the set where the value is bigger than t over 2. If you multiply it by t over 2, you get another upper bound, which is again the integral of the function over the whole space. And again, if you multiply by this, you get that. So that means this is not there, so you multiply and divide. That means another t goes in the denominator and another constant. So again, for the second part, you get an estimate of exactly this shape. So what have we succeeded in doing? And sorry, this wasn't super smooth. The idea is simple, but well, details. The measure of the set where this lambda is bigger than this t is bounded by this quantity. Remember, so far, we haven't used our key assumption that the continuous functions are dense in L1. And here comes that. Because left-hand side is independent of g. Look at this. There is no g here. It's all about the function f. Therefore, we get to choose our g. We can choose g such that, well, the density now is in this precise sense that the integral of f minus g in L1 over x is smaller than epsilon for any pre-assigned epsilon positive. So that is the type of density that we assumed, that for every given f in L1, there is a continuous one which in L1 norm estimates it as closely as possible. So from this, you get that this quantity is less than epsilon. So this means that for every epsilon positive, we showed that the measure of the set where lambda f is bigger than t, this measure is less than this constant over t times epsilon. But this means, epsilon being arbitrary and independent of t, that the measure of the set where lambda f is bigger than t is 0. Now we see that the t was also arbitrary, but t was also arbitrary, which means that the measure of the set of all values where lambda f not away from 0 is just positive must be 0. And this trick we have seen before, which is a very common trick. So the set, if this set was to have some positive measure, then one of these should have a positive measure for some I in the integers, right? This set is a subset of the union over all natural numbers where lambda f bigger than 1 over I, which goes to the simplest observation that a number is positive if it is bigger than some 1 over I for I in naturals. And this is countable. Each one has measure 0, so their whole union has measure 0. Okay, so we succeeded in showing that this lambda f is 0 almost everywhere. So that this lambda functional f is 0 almost everywhere. But that, by definition of this capital lambda, which is here, is exactly the statement of the Lebesgue differentiation theorem. This left-hand side is lambda, so it's 0 for almost every x. So that's one application, one cool application of the maximal, just the weak type estimate of the maximal function theorem to proving this important Lebesgue differentiation theorem. Later we will see why Lebesgue differentiation theorem itself is so significant. Until then, have a great one and thank you.